Hi everyone, thank you for tuning in to another video to learn about features in FHI-aims, an ab initio material simulation package for material science and chemistry. Today I want to talk about thermal conductivities for anharmonic solids using the Green-Kubo methods. The results I will show you today have been obtained with FHI-aims and are published here. A written step-by-step tutorial to obtain these results is also linked in the description. Please have a look there if you really want to learn how to do the post-processing and calculation of the following results. When we think about heat moving through materials, we often imagine a rather simple picture. Atoms are vibrating like they're connected by springs. This harmonic-like approximation works well for many materials. But what happens when reality is more complex? Traditional methods like the Boltzmann transport equation treat anharmonic effects as small perturbations. But in some materials, like copper iodide, this assumption breaks down dramatically. In copper iodide, even at room temperature, copper atoms show large deviations from the harmonic behavior. These aren't small vibrations anymore, they're significant movements that can even lead to temporary defect structures. Let's look at what this specifically means for thermal conductivity. When we calculate the thermal conductivity of copper iodide using the Boltzmann transport equation, we get a value of around 5.9 Watt per meter Kelvin. The experimental measurement, however, shows that we should get a value of around 1.68 Watt per meter Kelvin. That's a drastic overestimation of the experimental value by more than 350%. Now you might ask yourself, why do we have such a large discrepancy? Well, the Boltzmann transport method and similar perturbative approaches simply can't capture the extreme anharmonic behavior in this material. And this is where the Green-Kubo method comes in. Instead of treating anharmonicity as a small perturbation, we use molecular dynamics to capture the full dynamics of the system and directly count for all orders of anharmonic effects. During the molecular dynamics simulations, we can then also directly measure the heat current fluctuations and, with the Green-Kubo approach, calculate the thermal conductivity. In the work by Knoop et al. From 2023, several ab initio MD simulations were performed with FHI-aims using the PBE solve functional for this copper iodide system. The post-processing procedure and resulting plots are all implemented in FHI-vibes. When applying the Green-Kubo approach to copper iodide, we now see that we actually get a thermal conductivity very close to experiment with a value of only 1.9 Watt per meter Kelvin, which is indeed much closer to the experimental value compared to the Boltzmann transport equation approach. We can of course also take a look at the molecular dynamics trajectories to see in more detail why the Boltzmann transport equation here fails. Shown in this plot is the anharmonicity measure introduced in the work by Knoop et al. It relates the strength of the anharmonic forces compared to the total forces. A value of 0 corresponds to a perfectly harmonic system. In copper iodide, this measure stays around 0.5 for long periods, indicating that around 50% of the interactions stem from anharmonic effects. But on top of that, we observe that the anharmonicity measure can jump to significantly higher values, for example here. In this regime, the harmonic approximation completely breaks down. Copper atoms here temporarily leave their lattice sites, forming short-lived Frankel defects, something the harmonic approximation could never capture. To conclude, we find that the Green-Kubo method implemented in FHI-vibes provides a powerful tool for accurately predicting thermal transport in strongly anharmonic materials. And this capability is particularly crucial for understanding and designing materials where traditional perturbative methods fall short. If you want to learn how to obtain the results I just showcased, please look at our written tutorial with step-by-step instructions on how to compute the thermal conductivity in copper iodide from the harmonic approximation and the Green-Kubo approach. The full tutorial is linked in the description. Thank you for tuning in. Please check out our website and online tutorials for even more examples. Happy simulating!